modal logic, which is called Loeb's theorem. And he translates it into a funky kind of fixed point in Haskell. So to stay inside of ASCII, he spells it Loeb in the Haskell, but we can consider that as being equivalent as the umlaut. So the idea is you interpret box as some arbitrary functor f. You interpret the proposition p as being some arbitrary type variable, and you pick functor because it's something that gives us a little bit of structure. So he just sort of picks functor a little bit arbitrarily and gives a translation for it as a kind of interesting bit of knot tying. So knot tying is hard. I want to just put that out there as we're working through the way this definition works. So what happens here is we hold on to an FA that's going to be of type FA, and we say, so suppose we already have an FA. We've got this whole container full of functions, and for each function in the container, we're going to apply it to the eventual FA that we hope to get out of this fixed point. And if you swap in the FA and apply each FA to A to that, then we get an FA. So to make this more concrete, or rather, let's make it abstract first. So this is indeed a kind of fixed point, but I would say this is kind of pointless. So to make it more concrete, let's instantiate f as a functor, some arbitrary functor like list. I think list is a pretty good suited functor for this because spreadsheets are the analogy that Poponi gives to explain the behavior of Loeb. That is to say that Loeb acts as a kind of spreadsheet evaluation over the functor that you're playing with. So, and what happened to my pointer? So, we have this list full of functions. So if the first function is the length function, remember each function is defined in terms of the result of the entire recurrence. So the length function takes the length of the entire result, that is to say 3, and gives us that. And the bang bang 0 gives us whatever the 0th element of the result is, that is to say 3. And then we can add together the 0th and first elements of the result to get 6. So this works really nicely. And it also works really not nicely, which is how we would expect when we give it something like this. So the length of the list is 2, and the second element of the list is the sum of 2 and 2 and 2. So some recurrences don't terminate, and that's what we would expect because some recurrences don't have this uniquely defined solution that we need to be able to give any kind of answer. So there are a lot of interesting recurrences that we might want to be able to represent with this kind of fixed point. And it does generalize. There are all sorts of interesting things you can get if you pick a different functor. For instance, if you pick the identity functor, then you recover, well, the ordinary fixed point operator. But you can do a lot of other cool things. And I thought when I was playing around with this that maybe I should just pick some classic recurrence sequence, like, say, Fibonacci, and try to implement it in terms of Loeb. So I did, but it's a little messy. So you have to sort of fake relative references in terms of absolute references in order to implement this function. Because if you examine the definition of Loeb, again, if I back up, every function inside of this container gets past the exact same FA. So you have to scan into the list of Fibonacci numbers and dereference the ones that you care about. You don't have any notion of the elements of the sequence to my left. And this works, but there's a bit of a problem. And the problem is what Richard Bird calls the disease of indexitis. And some symptoms of indexitis include acute asymptotic inefficiency. So right here, we have to use this dereferencing operator, which costs us a factor of O of n. And in fact, in general, relative references within this framework must pay an extra O of n tax for every dimension of the functor that they're in. So also, this syntax isn't that great. Like, why do we have to go through this encoding? So these were sort of my motivating examples for why we should sort of proceed further and dig deeper into the original modal logic to try to extract a fixed point that has some more desirable properties in terms of operating with relative references. So in the hopes of trying to find a way to fix this, let's take a closer look at the axioms in the logical world where we can prove Loeb's theorem. So in particular, we can prove Loeb's theorem in K4 modal logic augmented with modal fixed points. And I'm going to kind of hand wave a little bit about modal fixed points. The details are in the paper. But the proof requires that we have this axiom 4 and this distribution axiom and the notion of a modal fixed point, which I'm going to model just using the ordinary term level fix operator in Haskell. And there are some caveats to that, but again, they're in the paper. So the search proceeds. The idea is let's try and find some Haskell structures that mirror these axioms, put them together, and then hopefully derive a fixed point that's closer in nature to the original proof of Loeb's theorem in logic land. And by drawing that Curry-Howard correspondence, then maybe we'll find something interesting. And maybe, just maybe, it'll actually satisfy our search. So in looking for these types, I went hunting through Hackage, and I found this Comonad class, which has a method called duplicate that looks really similar to this axiom 4 of K4 logic. And I found in the very same package this splat operator, which you'll recognize this type. It looks very similar to the type of a similar shaped operator from applicative. But we don't have pure, and it turns out that pure messes with all of the logical interpretation anyways. So it's a nice coincidence. It's actually more than a coincidence, but it's nice. And then we can use fix at a specialized type to simulate modal fixed points. So the idea is that we just want to play type Tetris and fit together all the puzzle pieces so that in the end, what we get is something with this type signature, which is the same type signature that Piponi originally has, but we give it more structure because we're changing the constraint from functor to Comonad apply. And if we play type Tetris, what we get out in the end is just this, which we can pointlessly translate to a nice, elegant, and intuitive definition. So some of you might be wondering, actually, what is a comonad and what's a comonad apply? And the best way to define this is, in my opinion, to give an example. So the comonad that I'm going to pick is a two-ways infinite stream. That is to say, a zipper into an infinite stream, where we have an infinite amount of A's to our left, a single focused A at the center, and an infinite stream of A's to our right. It looks something like this. And so when we're sort of located at a single focus within this tape, we can move left and we can move right. We can sort of pull ourselves along by a rope. And adding a little iteration function to build such tapes, we can derive a comonad instance for it, where extract just means that we take out the single element at the focus point, and duplicate means that we iterate these movement functions. So if you look at the type for duplicate specialized to tapes, it means that we've got to take a tape of A's and turn it into a tape of A's. So we just do that. But that's not quite right, because this fails to satisfy a bunch of the comonad laws. So what we actually do is we diagonalize the tape. And as you can see, what this means is that the original tape that we duplicated shows up along the horizontal, so that effectively the movement functions will commute over duplication. We can also define a comonad apply instance for tapes, which looks, if you're familiar with the zip list type, it looks just like a zip list. So we zip together the two tapes by applying each function individually to the argument to which it corresponds, and then giving us a tape of functions applied to their arguments of type B. So we can use our intuitions about these parts to build a bigger intuition, compositionally, for how L-fix works. I'm calling L-fix the fixed point that we're searching for. I'd call it Loeb, but the name was already taken. So to do this, I want to first build an example of how a one-dimensional spreadsheet with a tape might look, and then try to evaluate it one step at a time so we can actually see how this fixed point works on this particular choice of a comonad. So the idea is I'm trying to compute the integers. So I start by defining, well, what does it mean to talk about the value to my left? Well, the value to my left just means that I move my tape head one to the left, and then I pop out whatever value is there, and symmetrically for right. And then I define these p, z, and s functions, which are suggestively named, because p just says, well, go one right and pull out the value there. Z means, well, give me a 0. And s just means, given a tape, go one left and take the successor of that. So this tape here just means I'll have a tape where all the way to the left are numbers where they are the predecessor of the number to their right. And in the middle, I have 0. And on the right, I have a bunch of numbers, each of which is equal to the successor of the number to their left. So I think that's the integers last time I checked. And putting these together, we can look again at the definition of L-fix and try to step through what happens. So we say, at first, let's assume we already have the result. And the result in this case, as we've sort of manually reasoned through, is the tape of integers. And it's also of type tape of integers. But don't worry, this isn't dependently typed. I'm not really saying that. It's a pun. So we can duplicate this tape. And then we bring in our set of our tape of functions, our W of WA to A, or tape of tape integer to integer. And then all we have to do is apply each one of these functions to a different view on the tape. That is to say, each one of these functions sees a view on the tape that is localized to its own location. So this predecessor is going to say, okay, well, I will look one to my right, and I will take the predecessor of that, giving -2. And this predecessor is going to look one to its right and take the predecessor of that, giving -1. And then if we actually evaluate this, we get the same tape that we started with. That is to say that this is indeed a fixed point, because if we unroll this one more time, I mean, we'd have to turn it 90 degrees, but we'd get exactly the same thing. So with a little bit of syntactic sugar, we can revisit the Fibonacci sequence that we were looking at earlier, just defining a couple of little functions to slide the tape left by a certain amount and dereference a particular cell. And this is efficient now because of the zipping structure of the L-fix operator. In particular, we will evaluate every cell in this recurrence at most once. And we only have to pay for relative references based on how far away the relative reference is, not based on how far away we are from the absolute origin of the data structure. Because since we're inside a zipper, there is no real sense of an absolute origin of the data structure. And more generally, since every zipper induces a comonad, we can do this with a vast variety of structures. So inside of any zipper, but also inside of all the other different things that form comonads. And we can evaluate this, and as we expect, we get the Fibonacci numbers, but just a lot faster this time. So in the paper, I show how to generalize this to a bunch of different dimensions, that is to say, all of them. So you can nest together a tape of tapes and talk about a two-dimensional spreadsheet, or a three-dimensional one, or a four-dimensional one, and that's as many dimensions as I named, but you can keep going. And I give a bunch of utility functions for naming directions, and a little DSL that lets you interpret n-dimensional references into movements within tapes, and a single function with a very complicated type that lets you insert a possibly finite fragment of a sheet into an existing sheet. So as I said, the details are all in the paper and in the code. But with that little DSL, we can put together multi-dimensional references and evaluate them with the same kind of asymptotic complexities. That is to say that we still only pay for relative references as far as we move from the start of the relative reference, and we only evaluate every cell inside of this comonad at most once. So Pascal's triangle, what does that look like? Well, if you turn it 45 degrees, you have ones all the way across the top, you have ones all the way going down in the column, and then everything inside of that triangle is just equal to the cell above it plus the cell to its left. And there you go. And to conclude, I'd just like to show an example of a slightly more complicated comonadic computation. So the sort of canonical comonadic computation, or non-trivial comonadic computation that shows up in a lot of the literature is this thing called the game of life. And here we go. So all you have to say is that cells are either dead or alive. A universe for the game of life is a three-dimensional spreadsheet where two axes model the spatial axes of Conway's game of life, and the third dimension is the infinite evolution of that universe through time. And I'm not going to walk through all of the code, but the gist of it is that we insert, by the way, is that very complicatedly typed function. We insert a starting universe that consists of this two-dimensional seed of cells into a blank universe that's filled with this Conway's rule, and I actually parameterize over the rule set. But you can see that it's pretty intelligible. If you look at the neighbors, well, you just say the neighbors of a cell, the number of neighbors rather, are the length of the cells which are alive, composed with the cells that border the cell that we're talking about. And so I think that this is a relatively intuitive way of talking about these kind of recurrences. And to put it all together, we can evaluate this entire universe in 3 dimensions, 2 spatial and 1 temporal, and say what happens when we release a glider into this empty space and let it fly off across the universe. So the paper is all online, and in particular, it's executable literate Haskell. So you can read the PDF, or you can play with it yourself in your own REPL. So thank you very much.
This is not so much a question as just for at least 8 years, it's been the case that people will show up to Haskell IRC and say, I learned about zippers and they're really neat, and now I want to use them to model maps. How do I do it in 2 dimensions? And the answer has typically been, yeah, well, and now the answer can be, have I got a paper for you? So I want to thank you for that, because this will answer a lot of questions for a lot of people all the time.
You're welcome.
In the paper, I believe you mentioned that it's not just time optimization, it also gives different results from loob in some cases. Do you have a small example, perhaps using the tape Comonad, where it does give different results?
Right. So actually, it'll give different results whenever you rely on relative location. You notice how I had to encode a notion of relative reference when I was initially talking about the Fibonacci numbers. But if I had some, so I mean, like tape is a functor because it's a comonad. So if I ever talk about the cell to my left, that's always going to be the cell to the left of the original origin of the tape, rather than to the left of the function. But if I always think in terms of absolute reference from the original origin of the data structure, then they're going to be identical. So they do indeed have different semantics.
All right, I have one actually.
Okay.
So if you use a sort of like the skew binary random access list, where you, instead of just a straight list, you should be able to drop your n time distance to your neighbors to log n. Just, or maybe it's more of an observation than a question.
That sounds reasonable. That would be really cool.
So you, in the streams package, there's an infinite zipper that should have those semantics. So.
Yeah. I'll have a look at that.
That's everybody. Thank you very much.